We saw in the last unit that probability is counting. While this is always true, we need to understand the experiment to know how to count properly. When we flipped a coin, each flip was independent of the others. The coin has no memory. The coin looks the same before and after each flip. Imagine we're drawing marbles from an urn. We can set the experiment in two very different ways. The first way is to draw one marble, note its color, then return it to the urn. Draw a second marble, note its color, and return it to the urn. Finally, draw for the third time and note the color of the marble. For the second way to do this, we can reach in and take one marble, set it aside, then reach back in, take the second marble, and then set it aside, and finally reach back in for the third time and take the last of the three we wanted to draw. We can now note the colors of the three marbles that we have taken from the urn. Clearly, the fact that we returned the marbles after each draw in the first way changed the way we count. This case is like flipping the coins. At the beginning of each draw, the urn has the same number of marbles. These events are independent. However, in the second case, when the marbles are taken out and kept out, there is an important difference. In the first case, it is an independent event from draw to draw. What happens on the second draw is independent of what happens on the first draw, and so on. In the second case, what happens on the second and third draw is dependent on the events that went before. What happens on the second draw is contingent or conditional upon what happened in the first round. These are dependent events. Formally, the way to capture these issues is written as two events are independent if the following are true. Case 1. The probability of A given B equals the probability of A. Case 2. Probability of B given A is equal to probability of B. And case 3. The probability of A and B equals the probability of A times the probability of B. We read this notation for case 1 as probability of event A given event B happened equals the probability of A. The vertical line is read as given and tells us what the probability that A will happen if we know that B has already happened. In the case of flipping three coins, this would be, what is the probability of head happens on second flip, the event A in the formula, if we know that head happened on first flip, the B event in the formula? Obviously, what happened on the first flip is irrelevant to what happened on the second flip. Thus, they are independent of each other. The second case simply reverses the order of A and B. The last case, case 3, is much more interesting. Here we have an example of another important probability rule, the multiplication rule. We learned before, OR tells us to add the probabilities. Now we see that AND tells us to multiply the probabilities if they are independent of each other. The way we read case 3 above is the probability of event A happening and event B happening is the probability of A times the probability of B. This is true only if the events are independent. As an example, what is the probability of drawing a red marble from an urn with 5 red marbles and 10 blue marbles, and getting a head on one flip of a coin? These are clearly independent events, and thus we just multiply the two probabilities. 5 divided by 15 times 1/2 equals 1/6. Next, we have to consider the experiment that may have events that are mutually exclusive, meaning if one of them happened, then the other one could not have happened. The occurrence of one excludes the occurrence of the other. In the past, the probability of choosing a name off the college football team roster and also picking a person who is female is 0. Female was mutually exclusive of football players because all football players were male. Independence of events, dependence of events, and mutually exclusive events covers all the possibilities. Now we can develop two very important probability rules in depth as promised.